Thank you very much. Okay, so first of all, apologies for the last lecture. I took like a little bit of extra time. This time it won't happen because the next lecture is mine anyways. So, okay, so let me recap what happened in the last one, and I'll take it from there. I'll also like to clarify 2 points. One is, so last time we left at the following. So the problem I roughly stated was to evaluate either this guy, let me just put the limit here, which is going to be the clarification of, let me just write it this way, trace of pi s or r and fs fn rho. So again, we're fixing a dual group representation for this and a group G. So either this or the corresponding sum over primes. So I'm going to say 2 things about this. So N and S are relatively prime, and P is not in S of log P times the same thing, trace of. So this is where we roughly left at. So 2 things. So why did I write these 2 things? So one is this guy is actually what is calculating what we want. This is actually calculating the orders of the pole. In other words, this, if one can calculate this limit, this is supposed to be equal to what we wanted as like pi such that trace of pi s of fs times this order of the pole, m pi rho, times the multiplicity. So this would give what we want, whereas this would be more, and this is exactly where the clarification comes, pi such that there's still the multiplicity, there is the trace of pi of s fs, and then here, instead of the order of the pole, one would get the residue of the whole L function, the incomplete L function of s pi rho. So there are 2 things to be said about here. One is, as you can see, this is a more complicated expression. This has the residue inside, because we're summing. The difference, first of all, let's emphasize, is that this thing is summed over all integers, and this is summed over just prime numbers. So this is the difference between these 2 sums. And one is calculating the residue of the logarithmic derivative, the other one, which is the order of the pole, and the other one is calculating the residue of the L function itself. So I will come back to what is more natural, what is not more natural. It is unclear to me, actually, which one would be more natural. I'll make a comment about it in a second. But one more thing, which is actually a little bit more appropriate, is like, why is there these quotes? Why is this not an equality? It's because of the following fact. Well, although the order of the pole of the logarithmic derivative is always simple. Sorry, the pole at s equals 1 of the logarithmic derivative is always simple. Whereas the L function can have a higher order pole. That's very much so possible, and it would actually have higher order poles as this representation gets more complicated. So that is why there's these quotes here, because this limit for a higher order pole would not make sense. It wouldn't exist. If the order of the pole is 1, then this is true. If the order of the pole is higher, then there are logarithmic terms that I barely wrote over there that would have to be actually calculated. So in a sense, if one is taking the integer sum, one should basically look at the whole asymptotic expansion as opposed to taking the limit. That's one remark that I would like to, that I'll just verbally say and not write down. So basically this equality, in quotes, is an equality if and only if the order of the pole is less than or equal to 1. Whereas here, this is an actual equality. Well, then you would ask, why you bother with this? why not to take this? The reason is very much analytic, and maybe a motivation is the following. So why bother? Why bother with the sum over n, like the whole integers? The situation to keep in mind is the following. Suppose you were looking at a very simple-minded example, Riemann zeta function, okay? And I would like to calculate the order of the pole, like either the order of the pole or the residue of this function. The corresponding sum over the integers would be this, n less than x. So since this is 1 over n to the s, you're just summing 1. And as expected, this is just x plus, well, all of 1, basically. So this is just a reincarnation of the fact that this guy actually has a pole that this equals 1, and with residue 1. Whereas if you look at this sum, you're looking at primes up to x of log p. Whenever I say log, it is ln. Well, this is also x plus little o of x. However, this is the prime number theorem. So there is an extra very serious input to even calculate the sum over primes for the simplest possible thing. That's why we're actually giving ourselves the flexibility of summing over integers, because it gives the information that you want, even more than the information that you want, and analytically it sounds like it may actually be more feasible. That is why I actually even bothered putting this up there. So I hope this actually made a little bit of a clarification. I'll take it from here and I'll write down the trace formula now for one of these cases. I think I'll take this as my toy model, but like for this in the next class, I'll actually specialize everything to, so from now on, let's say, now on, so G will be GL2, and I'm going to put myself in the very, very specific situation where I'm going to consider these sums for a very specific set of automorphic forms. These are just holomorphic modular forms of full level of weight k. So fix a weight k. And consider holomorphic modular forms of weight k of full level. So sk of SL2z essentially. So then the Hecke operators act, and basically these traces, these ANs, where are those ANs? So these traces are basically traces of Hecke operators, the p Hecke operator acting on the space. I will tell you why I'm specializing to this in a second. So then if pi basically belongs to this space, if I look at Ls pi, this is the standard L function, and write it as a n over n to the s, and there's a very nice expression for the following. Then the sum over pi in this sk of 1 of a n is just by the Eichler-Selberg trace formula given by the following. I'm going to just write down these terms. It is a sum of 3 terms, actually. So the first one is the contribution of the trivial, the conjugacy class of 1, basically. So I'm going to tell you what this means. Okay, so this is term number 1. So k is fixed. K is the weight, once again. That's why it is appearing here. N is the n right here. This is term, let me call this term A, plus term B, which is minus a half times sum over d dividing n of the following gadget, the minimum of d over square root of n, and square root of n over d to the power k minus 1. And then there's the last term, which is c, minus 1 over 2 to the n to the k minus 1 over 2 times the following sum. Absolute value of m is less than square root of n, well, 2 times square root of n, times rho to k minus 1 minus rho bar to k minus 1 over rho minus rho bar times the following. F squared dividing m squared minus 4n HW of m squared minus 4n over f squared. Okay, why did I write all this in very explicit form? Let me tell you what this rho is. So rho is the root of the characteristic polynomial with trace m and determinant 4n. HW is what is known as the Hurwitz class number. And delta n of alpha is either 0 or 1, 0 if, or delta n of delta square of n is if n is not a square, and 1 if n is a square. So, okay. All right, let me just stop for a second and talk a little bit about what is going on here. Okay, so remember, we want to actually analyze these sums, either over the integers or over primes. It really doesn't matter. And I would like to put myself into this situation for the following reason. What's that? Question? It's not really odd. It's actually normalized so that Ramanujan actually, like the Ramanujan conjecture reads as 2. Yeah, so Ramanujan says an is 2. So this is, well, I mean 2 times tau of n. Well, just tau of n, I guess, right? Yeah, I believe so. In any case, the eigenvalues are of absolute value 1, not n to the k, or k minus 1 over 2. So there is a little bit of a normalization issue. So eigenvalues are just of absolute value 1. In any case, so normally, in both of these cases, I put this very harmless looking temp here, which creates a lot of problems because when you actually try to use a trace formula in trying to get an expression over the tempered spectrum, you immediately hit a bunch of problems. Because the trace formula inherently, like just intrinsically, gives a sum over the discrete spectrum, but not over the tempered spectrum. So one needs to basically take out all the non-tempered terms and non-cuspidal terms and everything. So that would basically create a problem. I will come back to that. But just to see the structure of these sums and how, for instance, like, is this more natural or is that more natural? Can we actually do anything? I think it's a good exercise to try to actually do this for the weight k holomorphic forms because they're isolated. So you don't actually have any of this temperedness problems because this is literally a sum over the tempered spectrum now. So I hope this makes sense. So it's a beneficial exercise to actually go over this. All right, so what we will try to do is the following. Once again, this is giving the sum over the trace of the nth Hecke operator over Sk for a fixed n. What we would like to do is to sum this thing over n. Or like over Pn with the log P factor. So either one of these cases. So we would like to take this expression, let me put a little n here, an, bn, cn, and what we would eventually like to do, is to calculate either this or the analog of that for the sum over primes of AP plus BP plus CP. So let me give these things names. So let's call this P of x for prime sum. And let's call this I of x for the integer sum. I just don't want to write the whole thing over and over again. Just I means integer, P means prime. Okay, great. Which one was that? Oh, this is holomorphic weight key modular forms of full level. Just holomorphic, yeah. So I'm hospital, yes, exactly. Yes. So hospital, holomorphic. Hospital, yes. Sorry. S is for the cusp, yeah. Cusp. Oh, God. So, S is German. S is German, exactly, yes. I forgot what it means, but it means hospital. What is it in German? Spitzen. Okay. It's like schnitzel. Let me also remind you what we expect in this scenario. So, reminder what to expect. Or let me remind you what we're trying to do with like summing these things up or whatever, either this or that. So this should calculate the residue of this, well, sum of the residues over pi, but like just in heuristically, residue of the standard L function of a cusp form on SL2Z at S equals 1. And this should be calculating the order of the pole of the same function at S equals 1. Since all of these are known to be holomorphic, we basically expect this thing to be little o of x and this thing to be little o of x as well. So, in other words, so I of x, so let me do this. You expect this. What's that? To be this, to be 0. Because L S pi for cuspidal pi is holomorphic. This is just to keep everything intact. So basically what we're trying to show here is if we can show that these limits are 0 just by looking at these sums, rather than actually employing all the Hecke theory or whatever. Because we would like to do this in general, obviously, not just for cusp forms. So this is a toy model, so to speak. But you're going to see that it's actually not that small of a model. Any questions so far? Okay, so the strategy is going to be the following. So I actually broke the strategy into 4 steps. And you're going to ask why each one of these steps is actually relevant. Well, we will see that as we move along. So step 1 is the following. I mean, as it stands, maybe I should also tell you, so this is the contribution of the identity conjugacy class. This is the contribution of the hyperbolic and unipotent conjugacy classes. Unipotent 1 comes in only if n is a square, and that is the one corresponding to d equals square root of n. And this is the elliptic conjugacy class that already appeared in Tasha's class, Tasha's lecture. So this is elliptic, hyperbolic plus unipotent, and unipotent corresponding to square root of n, if it exists, and this is the conjugacy class of 1. So, I mean, these, of course, are more generally true in any trace formula. The geometric side is going to be just sums of this sort. But remember, we're going to be, basically, this is a sum over n, and we're going to be summing this over n. The first thing is, I mean, as the way it stands, it doesn't resemble anything. This is a class number to start with. And maybe I should also make one more reference. This quantity right here is the class number and the orbital integral combined in general. So this is the orbital integral of the, so this thing is roughly the orbital integral orbital integral of the element with trace m, determinant n, times the class number, the volume of the same mn. We're going to see this in a second anyways, but one should basically, to put things into perspective, this is how these things look in the simplest case. So it's a sum over class numbers of a family, which is m squared minus 4n. But since we cannot just like sum class numbers, we need a workable expression. The step one is, let's get, all right, step one is just to rewrite the elliptic part. So rewrite the sum. And believe it or not, this just basically means you're changing the respective measures in calculation of all of these things. This appeared in Julia's lectures last week. And how it looks like is this elliptic part is going to be, so let's state a lemma here. Lemma in this color. And the first thing is the following. So the Archimedean orbital integral right here can be written as minus rho r to the k minus 1 over rho minus rho r is just a function of the following sort. M by root n. By the way, a warning today. These last two, I'm gonna write it down. I'm first giving the warning and then I'll write it up. Just 1 second. It will be a little technical, so just please stop and ask if something actually got wasn't defined or anything. Where theta infinity of x is the following gadget: I over 2 pi times x plus square root of x squared minus 1 to the k minus 1. I mean, these are very elementary calculations. X squared minus 1 to k minus 1 if x is less than 1, and it is 0 otherwise. So two things to note in this formula. One is, of course, these are fairly obvious for people who are familiar with the matter, but note that this is not a smooth function. Smooth function of x. And it looks like roughly something like this. At x equals plus minus 1, this has a certain kind of like cusp right here. I mean, it's not exactly like 90 degrees, but like it's not smooth. And this is exactly the structure of the singularities of orbital integrals over GL2, the Archimedean orbital integrals. The second thing is, well, there's not much of a second thing. We have this normalization factor. This is just a calculation. Okay, so let's keep moving. The actual thing that, the actual term that requires attention is this class number. And this class number can easily be rewritten by using the class number formula. So let me keep this. Okay. So lemma 2 basically says the following. Let me not rewrite the whole sum over there, but the sum over f of this HW of minus 4n by f is actually, this is f squared. Did I write f squared? Okay. Is just square root of 4n minus m squared over pi times L1 m squared minus 4n, where I'll define a generating function here. So LSD, this will be a weighted sum of Dirichlet L functions, will be a sum over f squared dividing d. I'll put this in a second. 1 over f of 2s minus 1 times L of s d by f squared. Okay. I'm sorry? Yes. So this is the Legendre symbol. This is the classical Dirichlet L function. So it's basically a weighted sum of Dirichlet L functions. And this, well, this goes back to Zaghi, because there's a history to that. But like this, for instance, comes up very cleanly in Zaghi's approach of the trace formula by this regularizing by an Eisenstein series. It just like comes up immediately, essentially. But all I want to say is, the elliptic part very naturally can be actually interpreted as a special value of an L function. And this is more generally true, I believe, for GLN. It just needs to be done. The corresponding work is already, resembling in Yun's work in Dedekind zeta functions of number fields, and well, Scheer also has, like Scheer's measures in volumes of tori, and the combination of the two should actually imply this in general. Like right now, this is just a consequence of the analytic class number formula. Okay, so that is great. Although I erased everything, I hope we have a certain, I'm going to keep this part. So all you need to remember from what I erased is the trace formula came as 3 parts for each n, and I'm just trying to rewrite the last part because it was the most kind of like cryptic part with class numbers and everything. Now this is a little bit more, like analytically more pleasant because it's an L function, and like, you know, these Dirichlet characters and stuff is like more manageable. So a corollary maybe is the following. The elliptic part, the C of n, is just sum over m in z, theta infinity of m by 2 root n times L1 m squared minus 4. So it's a very clean expression. Is it useful or not is a different matter. Okay, great. So far so good. We just rewrote the part Cn. Now, the next thing I want to do is, okay, so we rewrote, but like, would it actually be any useful? Like, you know, what would be, let me just see. Okay. Great. So we have a new trace formula. Okay. I mean, it's the same formula, but like we basically rewrote it. Now, what I want to ask is the following. Okay. So before I start analyzing C, let me start with analyzing A and B, because those were more explicit terms, and we'll see what happens when we're analyzing A and B. So a detour to, what about the sum over n less than x of an and sum n less than x of bn. Okay. So now let me remind you one more time, we are expecting the limit of this expression by dividing by x and letting x to infinity to be 0. So naively looking at this, well, this is a sum of 3 limits, and if the limit of the whole thing is 0, you may expect that each one of these individual limits to be 0. Apparently, if you're Bill Castleman, you would not expect that. Well, I did expect that when I was working on this first. Why wouldn't you expect that? Really? Would you expect these guys to be 0? So, well, let's take a look. Okay, so maybe lemma. The lemmas are in this color. So let me remind you what these terms are in dilemmas. Okay, first of all, the limit as x goes to infinity of the contribution of the identity term, well, this is 0, actually. And this is fairly straightforward to see because this thing is, so remember this an was, so recall an. So an was just k minus 1 over 12 times delta n by square root of n. So you can do an exercise, just calculate this sum. It is only non-zero if n is a square. There are not that many squares, basically. So this is just little o of 1, big O of 1. Okay, so this an does not contribute anything. Well, did you change your mind about bn? No. Okay, I'm waiting. Sure. Are you using this square root of n here? I mean, it's a fairly elementary calculation. Okay. Well, you're dividing by x and taking the limit. Okay, great. So, okay. Now, number 2. And recall that this was the contribution of the conjugacy class of 1. And the conjugacy class of the hyperbolic conjugacy class and unipotent conjugacy classes of Bn. Now, this is where things actually get a little hairy. So it turns out that this is actually a non-zero contribution. So this limit is non-zero. And you're going to see why I'm emphasizing this quite a bit, because, so let me see what the actual answer was for this, first of all. So it is 1 over 1 minus k. Depending on k, this actually has a non-zero limit. So I'm leaving these as exercises because they're just like fairly straightforward. But the actual upshot is, what's that? So this, what did you say? Well, yeah, but k equals 1 doesn't really have a trait. They're not isolated. So, yeah. So k is already like at least 2 here, but like the space is empty at least like if k is not 12, for instance. So, yeah, k is good. So, this hints at some certain complication. Hint at a complication, or the complicated nature maybe, hints at the complicated nature of Ix. Remember, Ix was calculating the residue of the L function as opposed to the order of the pole. And why am I saying Ix? Because, another lemma, if you actually look at this guy, so sum over p less than x of this, log p of bp, and take the limit of this, I believe this is 0. So if you actually look at the logarithmic derivative, it seems like all of these individual terms are 0, whereas when you're looking at the sum of the residue of the L function itself, which was kind of like more natural from a certain analytic perspective, it is a little bit more complicated. I mean, it has non-zero, non-vanishing terms. And this, maybe I should also tell you, so Bn, I was telling you, was a sum of hyperbolic and unipotent contributions. This is coming from the hyperbolic contribution. not the unipotent one. Yeah. So you may actually think that it is coming from unipotent because like it behaves weird, but no, it is actually coming from the hyperbolic contribution. So this already at this very kind of like crude point, we didn't even put our hands on the elliptic part of the trace formula, is hinting at some possibly complicated nature and distinction between the sum over integers and primes, which, I mean, one needs to actually take these things, like think about these things before trying to generalize, like if I take the integer part or if I take the residue or the order of the pole. I have also talked to actually, like, I had several conversations with other people, maybe more geometric people, and apparently this L function arises more like more naturally in geometry, apparently, but I can't say much about that. Mm-hmm. Mm-hmm. So the reason that this L function shows up is because of the following. So the Cn is the elliptic part. I think this appeared in Julia. So this is going to be just gamma's elliptic tori times volume of the centralizer times the orbital integral. So the choice of the function f is very particular here. We are basically choosing a function f, which is, of course, the unit element of the Hecke algebra at every finite place, except for primes dividing n. And at n, we are choosing this basic function to give what we're looking for. And this orbital integral basically corresponds to the sum over f, because, and the measure is the actual, like what measure are we putting in these orbital integrals? Usually one puts the canonical, what is called the canonical measure, which it gives measure 1 to the maximal compact, both at the torus and at G. If you do that, one gets the Eichler-Sadlock trace formula as I put over here. If instead one uses the measure that Tasha was using, the Tamagawa measure here, and geometric measures, one fixes a differential form for both G and T and calculates these quantities, one arrives at an L function. It's essentially, basically what's going on is the orbital integral is calculating, well, orbital integral times, if I set the volume of the torus to be 1, or like its Tamagawa number, so to speak, then the orbital integral is calculating a sum over class numbers of certain lattices inside. And these lattices are basically coming as orders in a orders of discriminant this, and their suborders. And that is why you're getting an L function right here. And as far as I understand, like I was actually trying to, like, this is one of the projects that one of the things that I want to mention at the very end. But this sounds like, it looks like at the very least, it comes very naturally in this Jacques-Zaki approach where they regularize this trace formula by hitting it with an Eisenstein series, and these L functions appear naturally from the Eisenstein series. And all of these L functions, I'm going to write this down in a second, they have functional equations, they have analytic continuation, they have beautiful functional equations. And I feel like that is a more natural playground for all of these things. I'll come back to that at the very end. There's no Eisenstein series yet. Mm-hmm. Exactly. So this is actually better expressed, this thing, as this zeta of, well, zeta, maybe I should say zeta of s m squared minus 4d for n, or zeta of s comma d, divided by, like, zeta of s or something. I mean, I think you need to regularize this, modify this a little bit, but like, roughly this is what one needs to do. There's no Archimedean part, yes. One should presumably put the Archimedean part too. I mean, that's a more natural object, just like look at the whole thing as, because the gamma factors are going to appear in they will appear in a second actually, and they will be very important for certain things. They will, for instance, give this contribution. This will come from an Archimedean factor, but for now, we have this. It's a little bit, so just to say, by the way, it's a little bit complicated. It looks very complicated, but to keep the analogy in mind, this m comma n tuple, corresponds to a gamma in GL2 of Q of trace gamma equals n and determinant gamma equals n. So just to keep the analogy. So this is with the elliptic part of the classical trace. So conjugacy class is an element. So this element gives you this guy. Okay. So now, okay, all right. So let's get back to where we were. So this was step one. We wrote down this elliptic part, and just to keep everything in mind, since everything else canceled, we're basically expecting a 1 over k minus 1 contribution from the elliptic part. Any question? Okay. Yeah. That's a very, that's a weird thing, yeah. Yeah, AP is, because, so AP is dominated by AN anyway, so, and AN is very small. Okay, so step two. Now the question is the following. All right, maybe I should just motivate you, but what I would like to do. So I'd like to do two things. I'd like to do a Poisson summation on M, where this is here. This is kind of like almost a reflex at this point, but there's a more general conceptual reason for this. But as an analytic number theorist, if you have sum over integers, you're just you want to do Poisson summation. A joke aside, there are other reasons. But this function very naturally fits in a Poisson summable setting. And then, remember, this is not what we're looking for. We want to sum this Cn over n. So that is the biggest thing. So we would like to do, so what are we aiming at? We're looking at the following. Poisson summation on M, for whatever reason, I didn't tell you. And then, after that, understand the sum over n of whatever the dual sum of this Cn. Okay, I hope this makes sense. So I'd like to first do a Poisson sum, and then I'd like to bring in the n sum and understand what the averages are. Because this is just an expression for a single an, I still need to average this over n. All right, so the only issue, of course, here is that this L function, if this L function was not here, I could just do a Poisson sum, and the result would be roughly something like 2 square root of n, and you would see that that is basically a contribution of trivial representation. It's a little bit of a hint of what's coming up, but we have this arithmetic factor here. What to deal with this? There's a pretty standard way of actually dealing with this you'll get roughly yeah. What's this? This. And as you see, if this was smooth, what's that? This is the Fourier transform. What are you doing? Okay. Oh, I am just give me some. It's like a Bessel function. It's but as you see, if C is actually non-zero, and if it was smooth, just pretend that it was smooth. Well, since we're pretending that this is not there, I may as well pretend everything's smooth. This decays very rapidly. The only contribution comes from C equals 0, so this will be roughly of square root 2n, so 2 times square root n. You sum it over n, you get x to the 3 halves. X to the 3 halves, then that limit does not exist. Oops. But we'll see. No, not really, actually. X to the 3 halves is the contribution of the trivial representation, which will not contribute over here. But anyway, so we will come to that in a second. Okay, so step 2 is this gadget called the approximate functional equation. And I'll be very brief about this. It's a technical gadget, and I'll tell you what it does instead of going into the details, because the details are not very illuminating. Approximate functional equation. So let's call this, let's give it an abbreviation, AFE. What it does is the following. It replaces, so what does it do? Okay, let me tell you what I want to do, first of all. So this is a Dirichlet L function. So you could roughly write it as, you could think of this as a, like m squared minus 4n by L over L. Okay? So roughly, this thing actually looks like the quadratic Dirichlet L function. So what I would like to do is to switch order of summations of L and M, and then break M into congruence classes here, and then do a Poisson summation. A very standard thing that one would actually do. Like, if you look at this type of sum for a second, what you want to do is, like, replace this by L, 1 by L, then A mod L of, like, A squared minus 4n, and then you want to do this. Okay? Just like so. So you want to do this, but of course you cannot do this, because the sum does not converge at all. Like, let alone it's not exactly this either, but that's okay. So what the approximate functional equation does is it gives a rapidly converging expression for that function over there, L1 m squared minus 4n. I mean, I'm writing it in this context, but approximate functional equation, maybe I should tell you in a second how it works. Let me write down what it does, and then I'll tell you. I'll comment on how it works in general. So there will be several choices of, like, auxiliary choices that are involved in the approximate functional equation. So I'll just write down what the end result is, and then I'll tell you. So lemma, maybe. It's a good word at this point. So lemma. So L1 m squared minus 4n is, okay, this is, I'm going to now write down the whole thing. F squared is dividing m squared minus 4n. This is coming from this F sum that already is here. 1 over F. There is an L sum. This is this L for each Dirichlet L function. 1 over L. Then there is this m squared minus 4n over L. That is divided by F squared. So for all practical matters, by the way, to keep up with the notation, just ignore the F sum. Just take F to be 1. Just think of this. It really doesn't matter. I mean, although F actually is a reminiscent of the orbital integral itself, it really doesn't matter what F is doing. You could basically assume that orbital integral is 1 for now. Times, so this whole thing is basically multiplied by the following. I'll tell you what F is before you ask. So LF squared over A plus, and I'll tell you what A is, LF squared over square root of, where's that thing? 4n minus m squared, h of LF squared A by square root of 4n minus m squared. Okay, so what's that? Oh, this is not square root. This is actually that times square bracket. Okay, what are these f's and h's? Okay, so f is a choice of a cutoff function. It really doesn't matter what it is, but it looks like the following. So if this is 0, 1, so this is x and y. So it starts life at 1, and it's like very flat at 1, and then it very rapidly decays, say, around 1 here, and its integral is normalized to be 1. That's for just normalization purposes. It really doesn't matter what you choose. As long as this thing decays rapidly, and it's a Schwartz class function, you're in business. H is a certain integral transform of f, I'm going to write in a second, which will also be rapidly decreasing, basically. For h and f, one should be thinking of a function that is supported like, roughly up to 1. So in other words, this is supported as long as LF squared is less than A, and this is supported as long as LF squared A is less than that. And A, what is A? A is just a parameter that we're free to choose. So this is a free to choose. But let me remark one thing. So A is not that free to choose because, so if you choose A to be very small here, that means there are only very few terms that contribute to the sum, but then that means there will be many terms that contribute to the other side, because it's, now there's a duality between A and 4nm squared over A. Or in this case, A and D over A. So the optimal choice is A equals square root of D, roughly. Let's keep that in mind. And I'll tell you what this H is now, which will be actually important in what follows. Okay, so this H, I'm going to define it as an arbitrary variable y. So h of y is the following: square root of pi over 2 pi I. As you can imagine, this all, like the whole approximate functional equation and everything actually comes as a result of a contour shift and Melon inversion. So this will be an integral at 1 of gamma of 1 plus u over 2 over gamma of u over 2. Oh, sorry, 2 minus u over 2 times pi y to the minus u du. Okay, so here is the Archimedean factor of the L function that is showing its face. What are the arrows? Oh, these are gammas. Okay, so it's the real part of real part of u equals 1 line. So it's a complex contour integral. I mean, it really doesn't matter. As long as these things converge, you can move on the right. I have some particular f in mind, but it actually does not matter at all, like what the choice of f is. Oh, there's supposed to be an f here, f tilde of u, sorry. Yep. Sorry, yep. There is, and f tilde is the Melon transform, so f tilde of no, it's the Melon transform. F of s, u to the s, du by u, ds by, whoops. Which way does it go? S to the u? Now I'm confused. Which way does the Melon transform go again? I must have written it up. S, oh, this is s to the u, I think, right? ds by s. Is that correct? I think so. E to the minus. It seems correct. Okay, good. Okay, so this is the Melon transform. What is important for us is for this kind of a function, so remark, f tilde of u has a pole, as a simple pole, at s equals 0 with residue 1. This is a normalization matter, so I'm choosing a specific s. F, choosing a specific s for this. So this pole is actually a general matter, but the residue being 1 is actually just a normalization issue. It also doesn't matter. But keep in mind that this guy actually has a pole at u equals 0, because in the second lecture, we're going to actually do a bunch of contour shifts, which will actually involve poles of the gamma function and poles of this function. And believe it or not, this extra contribution of this guy is going to actually show its face from a certain, well, let me not go too ahead of myself, but these will be important also in the general case of the general trace formula, where we need to actually isolate the discrete but non-cuspidal contributions or non-Ramanujan terms. These Archimedean contributions will actually be important. I'm sorry? So when we look at tomorrow, when we look at the more general form of the trace formula, and we would like to then get a formula over the tempered, the Ramanujan type, we would have to isolate the discrete but non-tempered terms, and for those, these guys will be important. Yeah. Okay, so great. So this is step 2. So what does step 2 then? We basically are going to take this. So let's take this and put it in a trace formula. So then this means this C of n can actually be written as f, 1 by f. This is over there, times L, I believe. Let me see. Or actually, let me not even write that down. So this is like, let's just go on to step 3 immediately. So step 3 is take this, replace the L1m squared that appears in Cn with this expression. I know it looks a lot more complicated, but believe it or not, it is actually not as complicated, or it's equally complicated, so to speak. And apply Poisson summation to the m sum. But we need to do one thing before. We had this extra parameter a that we were free to choose. Let me tell you in the last 5 minutes how to choose this in a way that would actually avoid a couple of problems. So, okay, digression. How to choose a. And this will be a little bit technical, but it is actually quite nice. So I'm going to do this over at this like FLF squared over a type. First of all, as we have discussed, if I choose a too small, then the second part of the sum gets longer. If I choose a too large, then the first sum gets longer. So the kind of like the natural choice of a, natural choice is choosing a somewhat close to square root of 4n minus m squared. And this is like the discriminant, basically, of the L function. This is the discriminant of the L function. Moreover, there's one more thing that I will... so remember, recall this Cn actually came as a sum over m of this theta infinity, the Archimedean orbital integral, times this L function. So the thing is, when I wrote the explicit expression for this, I said that this theta infinity was not smooth. So it's not very easy to do Poisson summation to a non-smooth function. It's not terrible. I mean, and also it gets smoother if you raise the level. So I fixed the level k forms. If you actually look at level 2000 forms, for instance, this will be differentiable 1999 times. You know. But just consider this. If I choose a to be actually this, what's happening? No, the square root is already in this. Yeah, square root has it. Because remember, it actually had the, it is in it. So this is discriminant times the orbital, regularized orbital integral. No, I defined this to be 0 outside that interval. That's why. So this is actually this. Anyways. Oh, this is missing. Okay. Sorry about that. My bad. Sorry. Yep. So when you put this expression in here, in particular, what you will be getting is the following quantity, theta infinity of m by 2 root n times f or h on the other side. So there are two sums, so I'm only writing one side. LF squared over this. Okay. Now this is the technical part. So f is very rapidly decreasing at infinity. And this guy has a singularity when the whole thing starts becoming 1 or minus 1. That means this has a singularity when m is roughly plus minus 2 square root n, at which point this thing becomes 0, so this actually decays faster than any of the polynomial. So in particular, this whole thing is smooth, or like very highly differentiable as a function of, well, m and n actually, like both of them. M. Well, n has an issue at 0, but so in any case, choosing a equals the square root of the discriminant not only gives you the optimal sizes of these sums in terms of L parameter, but also smooths out the singularities of the orbital integral. So it does two birds with one stone. And then I promised the organizers to stop in normal time, so I'm going to take it from here next time. Oh, I'm sorry.
Formula of GL2.